Time travel, a concept popularized by science fiction, has intrigued scientists, philosophers, and the general public for decades. While time travel in fiction often involves dramatic and paradoxical adventures, the scientific community approaches the topic with rigorous theories grounded in physics. This analysis delves into the theoretical foundations, potential mechanisms, and philosophical and technological implications of time travel. Time is a fundamental dimension in physics, intertwined with space to form the fabric of spacetime. According to Einstein's theory of relativity, time is not an absolute, linear progression, but a relative and flexible dimension affected by speed and gravity. Albert Einstein's special theory of relativity, published in 1905, introduced the concept that time is relative and can be altered by speed. As an object approaches the speed of light, time dilates, meaning it slows down relative to an observer at rest. This effect has been confirmed experimentally through observations of particles moving at high velocities and precise measurements of clocks on fast-moving aircraft or satellites. Einstein's general theory of relativity, published in 1915, expanded on this by describing how gravity affects time. Massive objects, such as planets or stars, warp the fabric of space-time, causing time to slow down near them. This phenomenon, known as gravitational time dilation, has been confirmed through experiments involving atomic clocks placed at different altitudes and in varying gravitational fields. Theoretical possibilities for time travel. Several theoretical constructs within the framework of relativity and quantum mechanics suggest that time travel might be possible under certain conditions. Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels connecting two distant points in space-time. If traversable, a wormhole could potentially allow for instantaneous travel between these points, possibly even to different times. The idea, first proposed by Einstein and Nathan Rosen in 1935, remains speculative due to the lack of empirical evidence and the challenges associated with stabilizing such structures. Challenges with wormholes. First, stability. Wormholes are predicted to be highly unstable and prone to collapse. Theoretical models suggest that exotic matter with negative energy density would be required to keep a wormhole open. The existence and creation of such matter are currently beyond our technological capabilities. Second, causality violations. Traversable wormholes could lead to causality violations, where cause and effect relationships are disrupted, resulting in paradoxes like the grandfather paradox, where a time traveler could potentially prevent their own existence. Time dilation and forward time travel. Time dilation, a well-understood consequence of special and general relativity, allows for forward time travel. An object moving at relativistic speeds or in a strong gravitational field experiences time more slowly than an object at rest. Thus, a person traveling at near light speed could theoretically travel far into the future while only aging a few years themselves. Closed time-like curves, or CTCs. A closed time-like curve is a theoretical solution to the equations of general relativity that allows for paths in spacetime to loop back on themselves, effectively enabling travel to the past. Proposed in the context of rotating black holes, known as Kerr black holes, and certain cosmological models, CTCs present intriguing possibilities but also significant challenges. Problems with CTCs. Firstly, paradoxes. CTCs inherently involve paradoxes, such as the grandfather paradox. Various theories, including the Novikov self-consistency principle, attempt to address these by suggesting that events in a CTC are self-consistent and cannot create contradictions. Secondly, quantum effects. At the quantum level, the behavior of particles in CTCs is not fully understood, and current theories struggle to reconcile quantum mechanics with general relativity in these scenarios. Quantum mechanics and time travel. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, introduces additional considerations for time travel. Quantum entanglement and superposition. Quantum entanglement and superposition hint at non-local interactions that could influence our understanding of time. However, these phenomena do not directly translate to practical time travel mechanisms, but suggest the interconnectedness and complexity of space-time. Quantum gravity and loop. Quantum gravity. Quantum gravity seeks to unify general relativity and quantum mechanics, potentially offering insights into the nature of spacetime at the Planck scale. Loop quantum gravity, for instance, posits that spacetime is quantized, possibly allowing for discrete time loops. These ideas are still highly theoretical and not yet supported by empirical data. Technological and energetic challenges. Even if theoretical models support the possibility of time travel, the practical implementation poses immense technological and energetic challenges. Energy requirements. Time travel mechanisms, such as creating and stabilizing wormholes or generating sufficient relativistic speeds, require vast amounts of energy, far beyond our current capabilities. For instance, the energy needed to manipulate spacetime or maintain a stable wormhole is orders of magnitude greater than anything humanity can currently produce. Engineering constraints. Building the necessary infrastructure for time travel, such as devices capable of achieving near-light speeds or constructing stable wormholes, presents significant engineering hurdles. The precision and scale required are beyond contemporary technology and may remain so for the foreseeable future. Philosophical and ethical considerations. Time travel, if realized, would have profound philosophical and ethical implications. Causality and free will. The ability to travel through time challenges our understanding of causality and free will. If the future can influence the past, as suggested by some interpretations of quantum mechanics, our notions of linear time and cause-effect relationships would need re-evaluation. Ethical implications. The potential to alter past events raises ethical questions about responsibility and the consequences of changing history. Ensuring that time travel is used responsibly and ethically would be a paramount concern. Experimental and observational approaches. While direct evidence of time travel remains elusive, various experimental and observational approaches continue to explore related phenomena. Particle accelerators. Particle accelerators, such as the Large Hadron Collider, study high-energy collisions that probe the fundamental nature of particles and spacetime. These experiments could potentially reveal insights into the conditions necessary for time travel. Astrophysical observations. Observations of extreme astrophysical environments, such as black holes and neutron stars, provide natural laboratories for studying the effects of intense gravitational fields on time. These observations help refine our understanding of general relativity and its implications for time travel. Conclusion. Time travel, as a concept, sits at the intersection of theoretical physics, technological innovation, and philosophical inquiry. While current scientific theories provide tantalizing hints that time travel might be possible under certain conditions, significant challenges remain. Theoretical models, such as those involving wormholes and closed timelike curves, suggest potential mechanisms, but practical implementation and empirical evidence are lacking. Future advancements in quantum gravity, particle physics, and cosmology may offer deeper insights into the nature of time and the feasibility of time travel. Until then, the idea of traversing the temporal dimensions remains a captivating blend of science fiction and cutting-edge theoretical exploration.